Alright folks, welcome back. This is video number 3 for section 10.11, finding Taylor polynomial approximations of functions. This should be a pretty short video, a couple of quick examples to finish up the lesson here. Example 6, the function f of x has derivatives of all orders for all real values of x. Selected values of f and its derivatives at x equals 1 are given in the table below. Write an equation for the fourth degree Taylor polynomial for f of x about x equals -1. So if we want to write the fourth degree Taylor polynomial, again, we're going back to what does our general form look like, and that's going to be, let's even do the fourth, come on eraser, at -1, we're going to find p sub 4 of -1 is going to be f of -1 plus f prime of -1 times x minus -1, or x plus 1 to the first, plus f double prime of -1 over 2 factorial times x plus 1 to the second, plus f triple prime of -1 over 3 factorial times x plus 1 to the third, plus f quadruple prime of -1 over 4 factorial times x plus 1 to the fourth. And then all we need to do is fill in the values of f of -1, f prime of -1, etc., which we can find all these values in our table right here. So our fourth order polynomial, that should be x, centered about x equals -1 is going to be, let's see, f of -1 is 2, f prime of -1 is -3, so that's going to be -3 times the quantity x plus 1, plus f double prime of x plus f triple prime of x plus f quadruple prime of x at that value. And then the last thing I would want to do is just clean up my coefficients here. We're going to have 2 minus 3 times the quantity x plus 1 plus 5/2 times the quantity x plus 1 quantity squared minus 4/6 or minus 2/3 times the quantity x plus 1 cubed plus 8 over 24, which is going to be 1/3 times the quantity x plus 1 to the fourth. And there's our fourth degree Taylor polynomial for f of x about x equals 1 there. All right, lastly, the last thing we're going to talk about, there are times when we might be asked, hey, what's the coefficient of the x to the 7th term in this Maclaurin polynomial? Or what's the coefficient of the x minus 3 to the 6th term in this Taylor polynomial? And you need to realize that when we're finding the coefficient of an nth degree term in a Taylor polynomial, we did it the same way for all of these. We had the derivative at that value divided by that number factorial. So it's f sub the nth derivative at c divided by n factorial. That's always the coefficient of our term in any of these polynomials. And so if I'm asked for one particular coefficient, I don't need to find all of the other coefficients along the way. I can just go ahead and find the one that I'm looking for. For instance, in example 7 here, find the coefficient of the quantity x minus 2 to the 4th term for the Taylor polynomial for f of x equals a natural log of the quantity 1 plus x generated at x equals 2. Okay, so 2 is our center, and we're finding it for the 4th power term, which means we're looking for the 4th derivative of f at 2 over 4 factorial as our coefficient. So in order to find this, we need to find the 4th derivative of our original function. So let's see, f prime of x is going to be 1 over the quantity 1 plus x. Then f double prime of x is going to be -1 over quantity 1 plus x quantity squared. And f triple prime is going to be 2 over quantity 1 plus x to the third. And f quadruple prime is going to be -6 over 1 plus x to the fourth. By the way, I'm always thinking about these as this, which makes it a whole lot easier to take these successive derivatives of them quickly and easily. So there's our fourth derivative at x. Now we want to find the value of that at 2 to put into our coefficient, and so this is going to be negative 6 over 3 to the fourth power, all that divided by 4 factorial, and so our coefficient is going to be negative 6 over 81 times 24, 3 to the fourth, and 4 factorial, and we can simplify that. We can take a 6 out of both of these, and we end up with the coefficient being negative 1 over 324. That's our coefficient of the quantity x minus 2 to the fourth term for this Taylor polynomial at x equals 2. All right, that brings us to the end of this video and the end of our lesson on finding Taylor polynomial approximations of functions. It's going to be really super important that you guys get a lot of practice in on writing these polynomials and working with these polynomials. It's going to be very important for you to do that because it's not the easiest thing to just, kind of watch somebody else do and then be good at it. You're going to have to put in some work to get good at this. All right, that takes us to the end of this lesson. Join us next time in video 1 for section 10.12, where we introduce the Lagrange error bound for a polynomial. All right, see you then. Have a great rest of your day, everybody. Bye-bye now.